Before the James Webb Space Telescope amazed the world with its breathtaking discoveries, another observatory was quietly preparing for a mission unlike anything attempted before. Now, its first observations are beginning to arrive, and they are revealing a universe far stranger than most scientists expected. The Euclid Space Telescope has started transmitting images with extraordinary detail and an astonishingly wide field of view. These aren't simply beautiful photographs of distant galaxies. They reveal enormous hidden structures, subtle patterns shaped by invisible forces, and evidence that the universe may be far more intricate than our current models suggest. Today, we'll explore what Euclid has captured, why astronomers consider these observations a major breakthrough, and how they could transform our understanding of the cosmos. As the mission continues, every new image has the potential to challenge ideas that have stood for decades. Unlike many famous space telescopes designed to study individual stars, planets, or colorful nebulae, Euclid was created with a much broader goal. Its mission is to chart the large-scale structure of the universe itself. Instead of focusing on a single spectacular object, it observes enormous regions of the sky while maintaining remarkable image quality. Launched by the European Space Agency in 2023 and operating around the Sun-Earth Lagrange point 2, roughly 1.5 million kilometers from Earth, Euclid enjoys a stable environment ideal for long-term observations. From this distant vantage point, it can continuously scan the heavens with exceptional precision. Its powerful optics allow scientists to observe millions of galaxies within a single survey while preserving fine detail. This unique capability makes it possible to study not only individual galaxies but also how they connect across unimaginable distances, forming the vast cosmic web that stretches throughout the observable universe. Perhaps the most remarkable aspect of Euclid's mission is that it is not only mapping visible galaxies. By measuring incredibly small distortions in the shapes of distant galaxies caused by gravitational lensing, the telescope helps researchers trace the hidden distribution of dark matter. Although dark matter cannot be observed directly, its gravitational influence bends light traveling through space, leaving subtle fingerprints that Euclid is designed to detect with unprecedented accuracy. In effect, Euclid is revealing the invisible framework upon which galaxies are built. It provides a glimpse of the hidden architecture supporting the universe, an enormous network shaped by matter that neither emits nor reflects light, yet dominates the gravitational landscape of the cosmos. When the telescope released its first wide-field mosaic, astronomers were immediately impressed by its scale. During a relatively short observing campaign, Euclid collected hundreds of exposures covering a region of sky many hundreds of times larger than the apparent size of the full moon. After combining these observations into a single mosaic, researchers uncovered an immense panorama containing millions of stars and galaxies. Even more astonishing is the realization that this early achievement represents only a tiny fraction of the telescope's planned survey. The completed mission will eventually produce one of the most comprehensive three-dimensional maps of the universe ever assembled. Every new observation expands that map, allowing astronomers to study the relationship between galaxies over billions of light-years while maintaining extraordinary image clarity. Scientists can smoothly zoom from enormous clusters spanning millions of light-years down to individual galaxies without losing significant detail. This combination of scale and precision is one of Euclid's greatest strengths, offering an entirely new perspective on how matter is distributed throughout the cosmos. Among the first regions studied in detail was the Perseus cluster, a massive collection of galaxies located roughly 240 million light-years away. At first glance, the image appears to contain countless glowing galaxies scattered across space. However, closer examination revealed something even more exciting. The observations identified hundreds of faint dwarf galaxies that had escaped previous surveys. These tiny galaxies are especially valuable because they respond strongly to the gravitational influence of dark matter. Their positions, motions, and shapes provide astronomers with important clues about where unseen matter is concentrated. The discovery of so many previously hidden galaxies suggests that our picture of the local universe is still incomplete. Even regions studied for decades continue to reveal new surprises when viewed with more advanced instruments. Euclid's observations also extend far beyond galaxy clusters. In nearby galaxies with low concentrations of heavy elements, astronomers can study environments similar to those that existed shortly after the universe formed. These ancient stellar populations preserve valuable information about how galaxies evolved over billions of years. The telescope has also delivered remarkably detailed views of globular clusters surrounding the Milky Way. Stars that once blended together into crowded patches of light can now be distinguished individually, helping researchers reconstruct the formation history of these ancient stellar systems with greater confidence. Elsewhere, observations of star-forming regions have uncovered extremely faint objects that may include free-floating planetary mass bodies drifting through space without orbiting any star. If future observations confirm these findings, they could reshape our understanding of how planetary systems form and how common rogue planets may actually be throughout our galaxy. Rather than presenting a quiet and orderly universe, Euclid's early images reveal a cosmos filled with constant motion, complex interactions, and hidden gravitational forces operating across unimaginable distances. And these first observations are only the beginning of a mission that is expected to continue transforming modern cosmology for years to come. Across every new region Euclid observes, one remarkable pattern continues to emerge. Galaxies are not randomly scattered throughout space. Instead, they gather along enormous filaments that stretch across hundreds of millions of light years, linking massive galaxy clusters into a vast interconnected network known as the cosmic web. For decades, astronomers predicted this structure using computer simulations, but Euclid is providing some of the clearest observations yet of how these immense patterns are distributed across the universe. The images reveal long strands of galaxies intersecting at dense nodes while enormous empty regions, called cosmic voids, separate these colossal structures. The scale is almost impossible to imagine. Every galaxy, including our own Milky Way, exists within this enormous framework. What appears chaotic from a distance follows an intricate gravitational design shaped over billions of years. One of Euclid's greatest strengths is its extraordinary ability to measure weak gravitational lensing. As light from distant galaxies travels toward Earth, massive concentrations of matter bend its path ever so slightly. These distortions are incredibly small, invisible to the human eye, yet Euclid's instruments can detect them with remarkable precision. By studying millions of these tiny distortions, astronomers can build detailed maps of where dark matter is located, even though it cannot be seen directly. Instead of observing dark matter itself, scientists observe the way its gravity influences everything around it.